Welcome back, students, to our Chemistry 1510 video notes. In this section, we're going to talk about lattice energy. So we just saw a figure of what a crystal lattice looks like. And in that crystal lattice, there were lines between the ions. And that's not really how it works. Really, what you see in a crystal lattice is something more like this, where you have a large negative ion and a smaller positive ion that are really close together, like touching. And ionic compounds are incredibly stable, and they're incredibly stable because they have this strong attraction between the positive ion and the negative ion, kind of like they're magnets, because they are mini magnets. So in this figure, the green is the chloride ion and the purple is the potassium ion. And so what we want to talk about is the energy that is released when these ions come together to form solid potassium chloride. And so that energy has a name, and it's called lattice energy. So there's one thing to be aware of, and that is when we're looking at the lattice energy, it's actually measured not when just regular potassium ion and chloride ion come together, but when these ions are in their gaseous phase and they come together into this lattice to form solid potassium chloride. So going from a gas ion to a solid is something that we can't measure in the lab. But what we can do is use Hess's law from a prior chapter to calculate what our lattice energy is going to be. So right here, this equation, if we were looking at our kind of Hess's law background, this would be our goal equation. This is what we would be shooting for as our final equation after we added everything together. So we would be looking for our two ions in gaseous form coming together to form an ionic compound that's a solid. This has a delta H associated with it, and that delta H is going to be the lattice energy, the energy released when this reaction happens. Notice how there's an L here to distinguish that this is a lattice energy. So there's a lot of equations that go into calculating this because this is our goal, but it's really not an easy thing to get to right away because what we're really starting with is a completely different equation. The equation that we're starting with is the enthalpy of formation of KCl. So the enthalpy of formation is going to be from elements in their natural state. So potassium solid, chlorine gas as a diatomic, forming KCl solid. So what we need to do is take this as our starting point. And first of all, we need to reverse that. So if you're paying attention to our Hess's law stuff that we saw in the past, you might be wondering why in the world would we reverse it when the KCl is on the product side here and the KCl that we want is on the product side here. And there's going to be a lot of equations involved in this. And if we reverse this one equation, then we only have to reverse one or two, whereas if we kept it the way it was, we'd have to reverse a whole bunch more equations. So it makes it easier to just kind of like keep everything straight. Plus, we're doing a certain method right now called the Born-Haber cycle. And so with that cycle, this is what they do. And what they do is they start with the KCl, and then our goal is to get to here. So in the Born-Haber cycle, he actually has his goal reversed. And so just kind of bear with me, and then by the time we finish all the reversing, it'll all come together. So we have the KCl as our starting point, and we are taking that KCl and we're turning it into potassium and chlorine gas, where this needs to be a 1/2 in front of it. And so when this happens, we remember our goal of we need to get to potassium ion in its gaseous phase. And so right now our potassium is not an ion and it's not a gas. So what we're going to do is use the sublimation, which is turning a solid directly into a gas. So we're going to use the delta H of sublimation to do that, to turn that potassium from a solid to a gas. Once the potassium is a gas, then we can use the delta H for its ionization energy to get to K+. Then our potassium is taken care of. It has turned from a solid into a gaseous ion, and that's what we wanted. Now we can focus on the chlorine. So in order to take the chlorine to chloride minus, first we need to break up the Cl2 into individual chlorines. This involves the bond energy of Cl2. So the bond energy is how much energy is released when a bond forms. And of course, you could look at it the other direction of how much energy is needed to break a bond. So depending upon the direction you're looking at, the definition of bond energy can change slightly. But what we want to do is employ that bond energy so that we're taking that Cl2 and we're breaking it up into individual chlorines. Once you have that individual chlorine, notice how all of these took energy, right? These were all additions. Now over here, when we take chlorine and we turn it into, from chlorine to Cl minus, what ends up happening there is now we're changing direction. Instead of adding energy, this is actually something that's going to want to happen. This is going to result in a release of energy. So we're going to use the electron affinity here for chlorine to turn chlorine into a plain old Cl in the gaseous phase to a Cl minus in the gaseous phase. So once we take all of these components and we put them together, the difference is going to be the lattice energy. So again, this process is called the Born-Haber cycle. It looks pretty intimidating until it gets summarized. And so now, as we look at the summary, there's an equation that we can use. And this equation is going to work with any ionic compound that contains a metal with a 1+ charge. And this is going to be the formula to calculate the lattice energy. So you're going to use the negative of the delta H of formation. You're going to use the sublimation, the bond energy for, breaking this bond here, the Cl2, the ionization energy for turning your metal into a cation, and then your electron affinity for turning your non-metal into an anion, where remember, a cation is a positive ion, an anion is a negative ion. So you would use this equation. Remember, we said that in the Born-Haber cycle, they're going to end up with the reverse of our goal. So what I mean by that is we were going to end up with, starting with KCl, going to chloride ion gas and potassium ion gas. And so because the Born-Haber cycle ends up with this, and what we want is the reverse of that, we end up reversing the sign here overall. So that takes care of making sure that our goal is pointing in the right direction. All right, so let's look at some trends in lattice energy. So first of all, if I didn't come back and erase this, then let's go ahead and delete that right now. Then let's focus on the lattice energy inside of a group. When we look at lattice energy inside of a group, remember that groups are columns on the periodic table. So no matter if we're looking at a group that has a positive ion that forms a positive ion like group 1 and 2, or if we're looking at groups that form negative ions like the halogen family or the oxygen family, we're going to see the same trend. That lattice energy is going to decrease, meaning that it's going to become less exothermic as we move down a group. So let's look at this first little bar chart. Here we have chloride in all of these, but what's changing is we're going from lithium to sodium, potassium to rubidium to cesium, which are all in group 1 on the periodic table, and they're in this order, right? So it's lithium, sodium, potassium, rubidium, and cesium. And so as we go down a group, what we're seeing in this trend is that the lattice energy is becoming smaller. So it's becoming it's going closer to 0, right? So it's less exothermic. The same thing is going to be true over here if we change to the halogen group, where the order is fluorine, chlorine, bromine, and iodine. So what's really happening here is that the bond length is changing. So bond length is the distance between, in this case, ions. And we're measuring from the center of each of these. So see how here we are at the center, here we are at the center, and we're measuring this distance. So as the size of the ion increases, like how we're seeing from lithium chloride to sodium chloride, sodium is bigger than lithium, the bond length is increasing. And with an increase in bond length, what's happening is that your magnets, right, so your ions, because your ions are just little magnets, are getting further apart. And when your magnets get further apart, they don't feel that same pull. And that really is going to have a difference in the lattice energy. We can quantify that with an equation. So this general trend relating to that ionic radius can be described with this equation. Now, this equation has a lot of variables in it that might not be super familiar to you. So the E that we're seeing here is the potential energy of your two charged particles interacting. The K is just a constant. The Q's are the charges of the ions. So maybe Q1 is the charge of your positive ion and Q2 is the charge of your negative ion. You would include the sign for each of those. And D is your bond length. So we can use this equation to start quantifying the energy that we should be expecting. So what we just saw how changing the distance makes a change in our energy, and see how the distance here is in our equation, right? So we said the greater the distance, the bond length, the smaller the lattice energy, and we're seeing that here mathematically as well. So then the other thing to consider is how that equation relates to the top part of the Q's. What if your Q's change? So here for lithium fluoride, if we look at that equation and we start solving, and I'm not going to actually solve it, but I'm just going to put in K here. Your lithium has a +1 charge, your fluoride has a -1 charge, and you're given the distance in this table here. Then for magnesium oxide, oops, let's try that again. There we go. Your Q 1 and your Q2 are going to change, because now magnesium is a +2, oxygen's a -2, and look, the distance, the bond length is quite, oops, I didn't think I was in black. Okay, let's try that again. Is quite similar, right? 209 to 212 picometers. Picometers are so small. They're smaller than nanometers. So these are so similar in bond length. But look at the difference in the lattice energy. And so that's coming into play from the charge difference. So notice how if we plugged in K versus for the lithium fluoride versus if we plugged in K down here and we actually solved for a numerical answer, what we would expect would be something that is fourfold, right? So if we look at K here, you're doing K times -1 divided by 209. Here, you're getting K times -4 divided by 212. So essentially what you're seeing is a fourfold difference between lithium fluoride and magnesium oxide's lattice energy here due to the fact of the charges. So the reason behind this is because those charges really are going to matter due to the fact that the greater the charge, the more tightly held those ions are going to be next to one another. And so that means when the lattice is formed, it's going to release so much more energy. So I think that is it for our lattice energy video. As always, thank you for your attention. This is Katoni signing out.